Hello, today I am presenting our ECCV 2024 oral paper, Made to Order, Discovering Monotonic Temporal Changes via Self-Supervised Video Ordering. Let me start by showing a time-lapse sequence of satellite images of Alaska over the past 4 decades. You can see that there are many changes. If you look carefully, you will see that there are 3 main types of changes. The ice cap retreat in the middle of the image is monotonic over time. The snow level on the mountains is changing seasonally, and there are some random variations in the lighting and shadows across the sequence. In this paper, we introduce a new task of monotonic change discovery. Specifically, given a sequence of temporal images, we want to detect only the regions that are monotonically changing with respect to time, invariant to periodic and stochastic changes. And the motivation behind this is that change is a continuous process, and current change detection methods only consider 2 images with a start and end point, without considering what changes are actually relevant over time. Here's another example of the construction of the Amsterdam Schiphol Airport. The monotonic change here is the construction itself, where the greeneries change seasonally. The main question is how? It's a fairly challenging problem, given that we want to discover the change, which means that we do not know the ground truth beforehand. The solution we propose is to leverage the temporal ordering in videos. The main intuition here is that only the monotonic changes can give rise to the correct ordering. So if the model orders correctly, it knows where in the images corresponds to that order. This also conveniently allows us to train the model in a self-supervised manner by shuffling the frames and asking the model to predict the correct order. From here, we just need a model that can both perform ordering and provide attribution. Let's look into the model architecture step by step. First, we discuss the model during deployment, where we feed the images to the model knowing the correct order. The input video sequence gets divided into patches and goes through a standard video vision transformer encoder, in this case a timesformer. The visual features are then passed to a transformer decoder, where each query represents an ordering index. The index will iteratively attend to the visual features. Next, we compute the cosine similarity between the encoder and the decoder features, and this allows the query to localize the monotonic changes by attending to the patches that correspond to the correct order. During training, we simply shuffle the frames and train the model to predict the order. We perform spatial max pooling from the attribution map to get the order prediction, and the loss is simply a cross entropy on each query. We show that our method works on a wide range of datasets and domains, from camouflage animals, time-lapse videos, satellite images, and longitudinal medical images. For each domain, we train the model from scratch and test on unseen sequences. Here are some examples of our results. Again, we train a separate model from scratch and test on unseen sequences as shown. Here are some more examples, where we also show that the attribution map can be used as effective prompts for SAM to obtain segmentation. To compare with change detection methods, we also create a new benchmark for monotonic change discovery. We show that existing change detection methods either under-segment to those that have already been trained on, or over-segment any changes regardless of their nature. Our method, on the other hand, can discover monotonic changes without manual supervision. In summary, we propose a new task of monotonic change discovery and have shown many examples, domains, and applications with more presented in the paper. We solve the task by using a proxy training task of temporal ordering and propose a transformer-based architecture that can do so. In the future, we hope to be able to capture more complex nature of changes. Thank you.